Okay, it's my pleasure and honor to introduce Dr. Murray Thomson. Dr. Thomson is a professor of mechanical and industrial engineering with a cross-appointment in chemical engineering at the University of Toronto. He's a VP and co-founder of Aurora Hydrogen, which is a company that's developing hydrogen production from microwave-driven methane pyrolysis. He has a Bachelor of Engineering from McGill, a PhD from the University of California in Berkeley. He's a fellow of the Combustion Institute, the Canadian Academy of Engineers, the Engineering Institute of Canada. He's on the organizing committee of the ISF workshop, the formerly the International Sitting Flames workshop, and on the editorial board of the Proceedings of the Combustion Institute. So his work has been very diverse over the years, but has a common theme. So he's studied soot formation, biofuels, combustion modeling, methane pyrolysis, and carbon material synthesis. So today he's going to give us the overview of progress and challenges in modeling soot formation in flames and reactors. I want to remind you that this is a topical review, so we have time for questions. So stay and have a robust discussion and argument, possibly with Murray. But please stay and engage in conversation after his talk. And let's welcome Murray Thomson.
Thank you. Thank you for the opportunity to present this. So first, just a note that there is a wide range of applications of the science of soot formation. And so we see, from a combustion point of view, soot is particularly motivated from air pollution, as we see on the right, 8 megatons per year. And it has a health effect. People breathe it in, and it causes a number of lung issues. Soot is also a contributor to climate change. It's the third most important radiative forcing. And heat transfer, soot plays an important role in radiative heat transfer from soot applications. But also, the science of soot formation is relevant to material synthesis, such as carbon black, other carbon nanoparticles, such as fullerenes and carbon quantum dots, hydrogen via methane pyrolysis in a number of applications is very relevant to or can be based on the science of soot formation. And even sort of a little more exotic is carbon stars. People have applied some of these concepts from soot formation to formation of pHs and carbon particles in the interstellar region near carbon stars. So the point I'm trying to make is that the combustion community has developed a very rich science on the area of soot formation, and this can be applied to a wide range of applications beyond simple flames. Now, these various applications have soot properties that are particularly important to them. So for instance, air pollution, the size of the particle is very important in determining its health effects. In the area of carbon black, it's determined by its surface area and agglomeration. That determines the type of carbon black. There are many, many types of carbon black. And so the point I'm trying to make is that in soot modeling, we don't just want to predict the soot volume fraction, we want to predict all these different properties. Some, such as soot surface properties, are fairly complex to predict. So just for maybe there's a few people who are not directly in the soot area, I just wanted to go over in one slide a very quick review of the big picture. So taking a look on the left there, in a flame, fuel comes in, it gets hotter. We have pyrolysis forming particularly acetylene and propylene and compounds like that. It forms the first aromatic ring. pH grows, forms compounds such as pHs. And then we have soot inception, the formation of the first particles, sometimes called nucleation. That is an area of very active research and a lot of discussion about what is the true mechanism of that. We'll talk about that in a bit. But eventually, by the time you get to, say, 3, 5 nanometers, you have something that would be an identifiable soot particle. It can collide with other particles, to coalesce to form a bigger particle, or maybe to aggregate into an aggregate with multiple primary particles. Surface growth happens, so pH can add to the surface, acetylene can add to the surface. It grows. As it gets to the top of the flame, it hits oxidizing species. So we have various oxidizing species that consume the particle, oxidize the particle. And the net difference between the formation and the oxidation is what's emitted from the flame. Okay? Now looking on the right, we have our aggregate structure there. A lot of primary particles. Sometimes this is described as pearls on a necklace, if you want. But the key parameters are the primary particle diameter, which when combined with the number of primary particles and P there, that gives you the surface area of the soot particle, which is obviously very important. And the aggregate diameter gives the mobility of the particle. One of the challenges in soot is often in soot models, we look at soot particles as sort of a generic soot particle, whereas in reality, the soot properties evolve as they move through the reactor or flame. So here we have at the very bottom, we have our soot precursors, then forming incipient particles that typically are liquid-like and quite reactive. Then they form nascent soot particles, then mature soot. Typically that's more graphitized. It also is less reactive typically. And then we have our oxidized soot particles. So the soot particle is changing, yet that's hard in a model. Often in a model we just use a sort of a generic soot particle. So that's a challenge for soot modeling. Just to show it on the right here, we see that as we move up the flame, first we have the increase of the incipient particles that eventually are converted into the mature soot particles. And if you look at the black line, that's the carbon to hydrogen ratio. So typically the carbon ratio increases as the soot particle matures. And that is one way of distinguishing them. Now looking at measurements, on the right there, as you move up the flame, you have different techniques there. So most common is laser-induced incandescence, and you can see that you're measuring a signal as you move up the flame. But typically LII is not very good at measuring incipient soot, and so aerosol mass spectrometry there, the green line, shows the incipient soot particles. And so we see that typically we miss that with LII. And so it's very important that these different soot properties, we keep this into consideration when we're comparing our model to our measurements, so that we're comparing apples to apples. Now there's many different processes happening at various scales. So at the molecular level, we have the molecular growth, and then a little bit larger scales, we have the formation of the clusters, maybe say a couple nanometers, then the primary particles at 10 nanometers, aggregates at 100 or more at once. And these are all contributing to effects that we see at the large scale. And there's different modeling approaches that can be used at different scales to better understand this. So we have quantum mechanics models for the molecular process, molecular growth, then molecular dynamics, which looks at the formation of clusters and our incipient particles, mesoscale models that look at aggregate, how the particles form in various aggregates, and then eventually we get to the classic continuum models where we model the entire flame. The focus of this talk is going to be on the continuum models, but acknowledge that the learning and insights and mechanisms developed in these smaller scale models, it's very important that that knowledge is used to develop the submodels that go into the continuum model of flames. And we'll talk about that more in a sec. So the objectives of flame modeling and reactor modeling is generally to understand soot formation processes in flames and reactors. Often when we do experiments, we don't get all the information, where there are gaps just because of experimental limitations. And models can play a role to supplement experimental measurements, to fill in the gaps, to better understand where the process is going on. We can predict soot properties of interest. We can also validate our current understanding against relevant experiments. So maybe at the very small scale models, very detailed models, come up with, for instance, a new model of Incipient. Then we can take that, put that in the continuum model, and see if it predicts the observed number of primary particles, and when it's in a very, obviously a much more complicated system of a flame with diffusion and all the various processes that are going on. Soot modeling is very complex. Often simplifications are needed. So it's very important to know what soot properties we're trying to predict. If all you're trying to do is soot volume fraction, a very simple model probably will work. But when you want to look at particle size distribution and soot surface properties, obviously a lot more complexity is needed. We have a wide range of experimental targets that we can use to validate these continuum models, these laminar flame models. So we have non-premixed flames. So we have co-flow flames, which typically have longer residence times, but can be operated at very high pressures. Omar Golder and his group have gone up to 90 atmospheres, I believe, at measuring soot formation. Counterflow flames have a shorter residence time and also allow us to move the flame around, so that's a good test of your model. Premixed flames, of course, we can control the equivalence ratio. Burner stabilized stagnation flames have good boundary conditions. Reactors, both shock tubes and plug flow reactors, are very useful. Obviously, very different residence times, different pressures and stuff. And people have used these to validate and improve and test their models. I think what's needed is to have models tested on a more wider range of conditions to just be sure that these have strong predictive abilities, these models, so that the more we test them at a wider range of conditions, the better we can be sure that this isn't just tuned to a particular condition. Now, in this talk, I won't be talking about turbulent and spray flames. Typically, those have to have their soot models are much more simplified in order to deal with the computational intensity and complexity of, say, for instance, turbulent flames. Now, our ability to model soot formation has improved rapidly over the last number of years, and part of that is by advanced experimental techniques that can detect and quantitatively measure, especially soot precursors, nascent particles, and the evolution of the soot. And I just chose a couple different examples, but on the left here, we have molecular structures of incipient soot by high-resolution atomic force microscopy by Komodo and the group at Naples. This gave a lot of insight into the soot precursors, their shape, their structure, and that really motivated a lot of new soot inception models, which is the most unknown part of soot formation. In the middle, Camacho and coworkers developed a series of flames where they measured particle size distributions with quite good boundary conditions to the flames. That was really useful because particle size distribution is a good test of a soot model, because you got to get the inception, growth, and agglomeration relatively accurately predicted in order to make your model agree with this. So there's really a step up in a challenge for modeling soot formation. And then on the right side is kind of an interesting one where you take secondary ion mass spectrometry and then you use statistical analysis such as primary principal component analysis to look at how the molecules on the soot surface evolve as they move through the flame. So this has really provided a lot of new understanding of soot formation, and that can be translated into flame models. The other one is detailed modeling at different scales that can handle the different length and time scales, for instance, molecular reactions, particle interactions, molecular reactions, particle interactions, and then eventually feed that into the large scales, the flames and reactors. And so just to pick two examples of that, I thought this was interesting. This is work by Vrecklock and co-workers where they were looking at soot oxidation, so quantum mechanics to develop better reaction mechanism for oxidation of soot particles. They developed a detailed oxidation mechanism. They validated it with a Monte Carlo one, looking at interaction with particles. Then they reduced it, and they used the alpha to connect it with a method of moments model. So now you've connected to a model that can be easily used in continuum models. I think this is a nice sort of image of what you can do. I think there's a lot of need, for instance, in the Inception models, there's a lot of proposals at the very smallest scales. And, but what we need to do is translate that into Inception models that we could apply for flames at the continuum level. Here's another sort of different example of this. So here, using discrete elements methods, looked at agglomerate processes of particles. And the idea here was to relate some simple variables such as number, density, surface area, and mass to some of the details of the soot morphology. And the idea here is that for a flame model, you could only predict monodispersed. We use a monodispersed model to predict number, surface area, and mass, but then use these correlations to be able to derive the aggregate structure, such as primary particle diameter, mobility diameter, and number of primary particles per aggregate. So I want to move on now to the sort of core of what at the talk. So here we're looking at the flame processes. There's a lot of different models that go into modeling a flame, and each one of them have a lot of submodels and stuff. We're not going to have time to talk about it all, but I'm going to look at ones that I think are of particular interest and relevant to some of the discussions in the soot community today. So first of all, starting with gas phase chemical mechanisms, we need a number of species in our soot model. Of particularly importance in the soot modeling is pH. And there are a number of models that I've listed here that provide pretty good pH species predictions. Typically, they have pHs up to 4 to 6 aromatic rings, which is a size that many researchers feel is relevant to particle inception. But they are computationally intensive. If we, just as an example, if we look at CREC from the Milan group, you have 450 species over 24,000 reactions. So these are computationally intensive. Developing these mechanisms is challenging because often using quantum mechanics to look at the rates and pathways is more difficult than for more simple molecules. And as far as experiments are concerned, validating them is challenging because often when you have pH, you have soot, and the soot interferes with a lot of measurement techniques. At the heart of any soot model is the Aerosol Dynamics model. So there are a variety of different approaches to solve the population balance equation. So there's integral methods, such as method of moments, that are computationally efficient, but typically they only give average properties. You have less information there. Then you have the discretization methods like sectional models, and they provide a lot more details, such as the particle size distribution. But they even, if you use a two-equation sectional model, you can even get some of the soot morphology, such as primary particle number and aggregate number. But it does take a higher computational cost. And then finally, there's particle tracking methods such as stochastic approaches, stochastic modeling. It's a very powerful one. It gives you a lot of, you can follow a particle, you can have very detailed processes. This has been highly developed by Marcus Kraft and the Cambridge group. But then the disadvantage of this is the high computational cost, and it is more tricky to couple the gas phase to the particulate phase. Looking at aerosol dynamics, there are a number of simplifications that are important to keep in mind. So your typical soot model assumes that you have spherical primary particles with point contacts. But if we look at TEM images, we see that primary particles are not necessarily spherical, and they also have necks. They're not joined at a point contact. researchers have looked at this, and under certain conditions, this can create a significant error in the soot predictions. Another assumption that is often used is a constant fractal dimension for the soot particles. And obviously that's not, strictly speaking, correct. The fractal dimension changes as the aggregates grow and evolve in the flame. Now, when two particles collide, they coagulate, and researchers have developed efficiencies, so not all collisions are successful. And so this is one by researchers at Tsinghua and Cambridge. It uses the potential well depth of the two colliding ones to calculate an efficiency. However, when they collide, two things can happen. They can either coalesce, so you see that on the left there, where they form one big particle, or on the right, where they form an aggregate. Now, typically, people use a size cutoff where they say below, say, 5 to 10 nanometers, we assume it's liquid-like, and they coalesce. Greater than that, they aggregate. But obviously, that's fairly sort of ad hoc. It would be better if we knew something about the soot particle. Again, rather than treating the soot particle as sort of a generic soot particle, we actually have information on that. For instance, is it liquid or is it more solid-like? One of the ways of doing that potentially could be if we track the carbon to hydrogen ratio in the particle, and that would give us more information about the soot properties. Now, probably one of the biggest topics of discussion in soot modeling is inception and how it's to form. Since the very beginning of soot, a lot of the modeling by Frecklock and Wang, we have two colliding pHs that stick together. And the assumption is often that this is a physical force that's keeping it together. But equilibrium calculations have shown that free monomers are dominant at flame temperatures, so it's highly reversible. And that probably wouldn't give us enough inception rate. Now, we could go to very large pHs, but the problem is their concentration in the flame is very small, so we're not going to get the number of primary particles that we would expect. So the question that many people are wrestling with is how to stabilize the dimer, yet at the same time have fast enough inception. And there are a number of different ones. I recommend to you a recent review article by Jacob Martin on exactly this issue. But I'm just going to mention a few ones. A lot of interest in resonantly stabilized radicals. Hope Michelson was leading that. Then from the Cambridge group, we have the curved pHs and the aromatic pi diradical ones. And then from Frecklock and coworkers, we have E-bridge pHs. All these are being proposed as a way to stabilize the dimer so that it can go on and become a larger cluster and have particle inception. What's needed from the continuum model, flame model point of view is we need to transfer some of these concepts at a very detailed level into models that we can implement into an actual flame model. One model that has been implemented by Reza Kolgi and coworkers is where you have a reversible formation of the dimer, so pHs collide and reversibly form a dimer, and then you have a chemical bond formation to make a stabilized dimer. And this possibly could be an approximation of, for instance, the aromatic pi diradical route, where you have a collision and then you have a bond forming. But we need to find ways to bring some of that detailed information into more flame models, which are happening at a much larger scale of modeling. Another question is the size of soot precursors. That has been discussed for a long time, and the debate is still ongoing. So there's been a lot of very interesting experimental measurements, so atomic fork microscopy, mass spectrometry. These are coming from the Naples group, and that has given us insight into what are the likely size of soot particles and their molecular structure. So I've just plotted up a graph there on the left showing various experimental results of people suggesting the number of aromatic rings in soot precursors. On the far right, we have models. Typically, models are 4 to 7 aromatic rings. And so we see that models are using soot precursors that are within the range that experiments are suggesting. However, let's say a little bit on the small side. Okay? However, there are new papers coming out suggesting that maybe even 1 to 2 aromatic ring pHs could be playing a role as soot precursors. So the debate continues and is still very vigorous. Another question when developing a soot model is where we divide between the gas phase and the particle phase. Typically, the chemokinetic mechanism just includes pHs, such as pyrene, for instance, up to there, and then stops, and then you have the population balance equation of the particle phase. Probably it would be better to include cluster growth in the gas phase mechanism, but at some point you need to move to the particle phase model, which would be more accurate. Moving on to pH growth, kind of a little bit like Inception, you have pHs colliding with particles to grow. From detailed thermodynamic calculations, the binding energy increases as the particle gets bigger, so pH adsorption is going to be less reversible than Inception. And people have used equilibrium concepts to develop efficiencies of pH absorption. So you see the equation there has the equilibrium constant and the concentration of pHs. And so you see here that as the pHs in the gas phase decrease, your pH absorption decreases also, or efficiency decreases. One interesting question is that can you get desorption of pHs from the surface? And Siegmann, quite a while ago, observed this, where he was seeing that his number of particles was going down, but the size of the particles was going up, and suggested that perhaps this is desorption of pHs off the surface. We did some measurements recently, and we found that even though young soot was forming, our pHs were increasing in concentration. And so it's an interesting question, not clear. I do note that the Little group did some modeling of this, and they found that you could get desorption of pHs, and that could have a significant effect on pH levels. But this is very much sort of an open question at the current time. Moving on to the growth, the classic Hacke mechanism, so Frecklock and Wang, that's looking at surface growth and surface oxidation. That's really well established, but one of the questions is about the effect of surface reactivity. So depending on the surface properties, you can get quite a dramatic change in reactivity. Typically, young soot is more reactive, mature soot is less reactive. And so different approaches have been. On the far right, we see the approach of Dworkin and co-workers with thermal aging. So the idea here is young soot, the reactivity is increasing, but as they get old, more mature as time goes on, the particles get less reactive. That's one way to do it. An alternate way was the paper that I talked about 3 slides ago by Frecklock and co-workers, where you consider the different sites on the soot particle oxidation. And just to show you that how surface reactivity is important, so here what we've done is we've preheated a bunch of soot particles at various temperatures in order to induce graphitization, carbonization of the particles. And you see that in a TGA, that you have to go to higher temperatures in order to get the oxidation. So the surface reactivity is clearly changing. Okay? And you can also do this in environmental TEM on an individual particle. And so here we see the same behavior. And the image there is a soot particle where the graphitic shell has been eaten away, and then what you see is in red there is the inner core. And so what this is showing again is just, we often in soot modeling, especially for flames, look at soot particles as all kind of generic, but in fact, different soot particles have different surface properties. Now, when we have oxidation, things can happen to the primary particle and the aggregate. So here what we see is particle aggregation. So particle fragmentation, so aggregates can fragment. And so what happens is as the oxidation eats away at the particle, it can break up into aggregates. And we see this on those images on the right there. So those are done in environmental TEM, and you see that the particle is being oxidized, being attacked, and the bridge gets eaten away, and eventually, that's what the bridge is what the arrow's showing, and then eventually it breaks apart and you have two aggregates. Now, Sirignano and co-workers have developed an aggregate fragmentation rate, and it's a function of both the oxidation rate and the particle morphology. Another thing that can happen is internal oxidation. So on the right here, we see the environmental TM image of internal burning. So oxygen diffuses in, and then you get these, in the middle image, oxidation tunnels coming in, and then eventually internal burning, and you have a shell formation. And so obviously this is, again, a challenge to Soot modeling, because often we look at oxidation as just happening only on the outside. That's very common in Soot modeling. But people have addressed this. So if we take a look at some of the work of Kaladesis, he's developed a model of internal burning. And so in this case, the oxidation rate times the sum of both the external area and then the internal area of the, like the pores and stuff. So that's for internal burning. Obviously, internal burning can generate primary particle fragmentation, and Sirignano and co-workers developed a model that was a function of the oxidation rate and the pore area, essentially. Now, I've talked about Soot modeling and some of the limitations and simplifications issues that are out there, but I want to come back and say, well, you know, but we've made a lot of progress. So if you take a look at this, we've been able to model particle size distribution, Soot properties such as carbon to hydrogen ratio, primary particle concentration, pH mole fractions, Soot volume fractions. We have been able to successfully model a wide range of properties of Soot, and that's a good news, right? However, what's needed now is to develop models that you can take the exact same model and apply them to a wide range of conditions and pressures and temperatures and still get good prediction ability. And that's something that still needs to be worked on. So the remaining challenges are well-validated pH mechanisms. We find that when we compare different mechanisms, often they give quite different results. The inception models that are being developed at a very detailed mechanistic level need to be transferred to the to continuum models, to flame models, so that they can see how they operate in a flame, where they predict the number of primary particles that we're observing. More needs to be done in predicting the evolving Soot surface properties and their effect on growth and oxidation. Again, as I said, accurate prediction over a wide range of conditions. But I also want to talk about new directions. So the combustion community has built up a very impressive amount of understanding and models and expertise in the area of Soot formation. And that can be applied to new areas. So on the left, we have our classic carbon black furnace process, where heavy fuel, heavy hydrocarbons are injected into downstream of a flame, and we form carbon black. But this forms a lot of CO2. An emerging process this is the monolith one, where we have methane with electricity going, and we get 100% yield of carbon black with no direct emissions. And of course, what we're forming at the bottom there is carbon black and hydrogen. There's a lot of interest in that. That's methane pyrolysis, a lot of interest. I've modeled for industrial partners both the carbon black process on the left and emerging methane pyrolysis approach on the right, not monolith, but other people. And Soot models work very well. I mean, they really add a lot and provide a lot of insight into people who are trying to understand these processes. So that's you know, definitely our expertise is relevant to these processes. But these processes are different. In a flame, very little carbon goes into Soot, but in a carbon black, you get 60% conversion. And this is an image in my lab here of a microwave-driven methane pyrolysis unit. And here you have 100% conversion. and you get very high particle loads, which is quite different. The other thing to keep in mind is that when you have 1 mole of methane, you get 2 moles of hydrogen. So you do get chemically induced acceleration of the velocity and or pressure rise just because of the chemical reactions. So future directions for soot modeling, as I see it, I think there's a need to transfer some of the very detailed models fundamental models into flame models. I think combustion is challenged by climate change and CO2 regulations, but aviation is likely to be running on hydrocarbon fuels for the foreseeable future. So there's an area where soot is particularly relevant. And I think there's a great opportunity here to transfer the knowledge base that we've accumulated over decades to new applications, particularly in the area of carbon nanomaterials and methane pyrolysis for hydrogen. With that, I'd like to thank Reza Kolgi and Nick Eves for their help on this, and the technical program chairs for this opportunity. Thank you very much.
So we have time for questions. I want to point out that there are microphones sitting in the aisle here and the aisle there, so you can come up to the microphone, and I encourage you to come up to the microphone and ask a question. Katharina, I see her has her hand up.
Katharina Kose, Bielefeld University. Thanks for a very clear and very well-structured talk, and for looking into details in a way that we can see the progress quite impressively. So thank you very much. I would like to pick your brain about a question that intrigues me since quite some time. And maybe you see it as controversial, but typically our community stops with the process when the soot is formed. And then we kind of rely, or different other communities rely on global parameters that we offer them, like a size distribution or so, for some real world problems. And I wonder, when you had your list of desirables, whether we have to add some in terms of transformations that we envision. So let me highlight, for example, the atmospheric pollution, the direct local pollution through the ultrafine particles and their health implications. So typically those people who model those and relate these to, number of hours that you could have lived healthy, they don't interact with our community, but they just do public health related models with some global parameters that are probably outdated. Next thing, if we look into sustainable aviation fuels, we're looking at different molecules from the ones that are emitting soot at the moment. Now, I see there is an ongoing debate, for example, on the influence of contrails from these fuels, and different people come to different conclusions. So if we stop at the particle once it's formed, it's probably not wise. So I'd like to incite a little bit of discussion on that. Thank you.
Excellent point. So often we stop, a few centimeters after the flame. We kind of end it there and say it's success. But obviously what happens like in an aircraft, in the exhaust stream, and then it goes outside, and then you have condensation of water and particles on it, and so it can change quite dramatically. In our ISF meeting, actually, just a few, a week ago, one of the comments was exactly that someone from the soot community went and talked to the people in the aerosol community and felt that their description of what soot coming out of an engine looked like was completely not relevant, not accurate. So you're right, I 100% agree. There needs to be communications so that the interface between what we think is, what we're measuring coming out of flames and engines and stuff is communicated to the atmospheric chemistry community, so that they're using ones. But it's a very good point. I think often it's at the interfaces where things kind of fall apart.
Ken Brzezinski, University of Illinois at Chicago, as you know. At the very end, you mentioned your methane pyrolysis reactor, and you have a company that you mentioned that you're involved in, and it sounded like this was a company to produce hydrogen, and the carbon black was a byproduct. Now, carbon black, as you know, has tremendous industrial uses. It's put in tires, used in many, many places. But how is the balance going to work out in the long term? The need for hydrogen to replace carbon-based fuels is so enormous that the quantity of hydrogen produced by this process would lead to an enormous amount of carbon black. Are we going to just take the carbon black and put it back in the earth from where it came from?
That's a great point there, and it's much discussed in the methane pyrolysis community. So if you're, so Monolith, which I did, which is the most successful methane pyrolysis company, they got $1 billion line of credit from the US government. So what they do is they focus on carbon black. And to a certain extent, hydrogen is a bit of a byproduct that they use to make ammonia from, but they really focus on the carbon black, which you need to do. But I've been told, like, so in Alberta, in oil refining in Alberta, they use huge amounts of hydrogen. And I think the number was, if they ran that, if they replaced that with methane pyrolysis in like 3 days or a week or something, they would do all the carbon black for the entire world, right? So you're totally right. I mean, the scales are just astronomical difference between the carbon you produce from carbon black and the hydrogen you need, right? So the market's totally imbalanced. The process that we're doing does not make carbon black. We make millimeter-sized carbon particles, and for that specific reason, right? Because there's not enough markets in the carbon black area. So we're focused on other markets, such as there are people looking at graphene for the cement industry. We also look at steel industry. There's a wide range, carbon fibers, and there's a whole group doing that. It's called the Carbon Hub in Houston, at the university there, and that's the Carbon Hub is looking at all this, like how do we bring sort of methane pyrolysis carbon into that, new forms of carbon so that it can be useful. However, one thing you can do is you could just bury it, sort of like a reverse coal mine, right? So you basically have a hole in the ground and you fill it with solid carbon. In many ways, compared to CO2, it's probably going to be very stable and very cheap to do. We've been moving around carbon, solid carbon, for centuries. So that's a good way to do it. But yeah, so very important with methane pyrolysis is that using pyrolysis to make hydrogen is very, very easy. But the carbon side of it is where all the problems start. Carbon is a very fascinating atom, and you can get all sorts of different structures, good and bad, when you're doing methane pyrolysis. And so that's where the differentiation is particularly strong, is what carbon are you creating? So anyway, it's a whole topic in itself.
I have another question.
Yeah.
For the diagnostics people in this room, what would you recommend for measurements to help improve models?
I think having, well, for modeling generally, well-defined boundary conditions is important. Rich data sets. So if you just measure soot volume fraction or something like temperature or something, I don't think that's really challenging for modeling. I think the more detail, the more you can get information on the soot particle composition, the particle size distribution, pH chemistry. The more it's a rich data set that challenges the model much more. I think also the bigger range where you look at a whole series of flames at different pressures, different temperatures, because that challenges the model. It's fairly easy to get models that work under very narrow conditions, right? But to get models that work under a wide range of conditions is very, very challenging. And I think that's where we need to go, is to have robust models that can work under a wide range of pressures and temperatures and premix, non-premix, and stuff like that.
Okay, let me ask a little bit of a detailed question about that then.
Yeah.
You mentioned this result that Pascal Degroo's group has seen with increase in PAH with increasing height in the flame. And we've seen this too in premixed flames, but not so much in diffusion, co-flow diffusion flames. I was wondering if you could comment on what you think was causing that, or maybe I misunderstood what you said.
Well, what we think might be happening, this is very might, so this is not, is that pHs are depositing on the surface of the carbon particle, reacting, maybe combining into larger structures, and then desorbing off. And then we see, so that was like Sigmund's work there on the far left of the graph that I showed, where he finds as you go higher in the flame, you get these bigger and bigger pHs, right? And so the idea is maybe this is the chemical reactions happening on the surface of the particle. This is sort of conjecture, but we definitely don't think that way when we do these models. We assume that when the pH goes on the surface, essentially it's gone. It's just part of the carbon. So again, it's looking at one of the simplifications and assumptions that is sort of embedded in the way we do soot modeling.
George Kelesidis from ETH Zurich, Switzerland. Thanks for the great talk. And following up on the comment from Professor Kose regarding how we can interact with the atmospheric community, after interacting actually with this community to get the climate impact of soot, it was clear to me that a large part of the current uncertainty regarding the soot contribution to global warming comes from the emission rates. So could you comment regarding how combustion models can help this community to have better estimates of the emission rates of soot?
Well, that would be definitely the type of models that I do. You're a long way from it, right? Because really you're really talking about engine models engine measurements, right? So the emissions are really based on the more complex processes that are happening in engines. The problem with engines is they tend to be a bit of a black box. You don't have a lot of information about what's happening inside. And that's where more fundamental models can really play a role, because they give us more insight into the details. But you're right, but when we're really looking at emissions, we're really talking about engine emissions or big fire emissions, like a forest fire or something like that. And granted, you're right, that's somewhat removed from these more laboratory flames that we're looking at. So I think each scale of the experiments and modeling has its value, and it's just important that we all talk to each other so that we can pass relevant information back and forth.
Well, if we have time to elaborate a little bit more on that, pressing aspect, I think it may not be needed to go through all the way from the gaseous, fuel to the actual, engine process in all of the detail, but to sort of try to, from the knowledge that is known now, to construct a model of, let's say, plausible engine exhaust particle characteristics, to then see how they would oxidize, how they would react with other pollutants in that same atmosphere, and then to go from there and not try to build it up. You kind of challenged and triggered this additional question, not to build it up from scratch with all these, scales in between. So is that more plausible?
It is, but yeah, we also have engine measurements. So we do have measurements in the exhaust of engines. So that's, but yeah, I think you're really talking at the engine scale when you're talking about emissions.
If there are no more questions, let's thank Murray for his wonderful talk.
One more.
Is there? Oh, yes. Oh, I'm so sorry. I didn't see you.
It's all right. I'm Michael Delicatios from Northeastern University. I would like to ask you, what is the relation of the smoke point with some model for soot formation? Have you done some work there?
Yeah. So especially with jet fuels, we've looked at smoke point a lot. It's the smoke point is based on basically a wick burner, I believe. Although I know the group at Yale has come up with more sophisticated versions, but the original is a liquid fuel one. So it's a fairly it's a very industrial measurement. So but especially the group at Yale has looked at translating fundamental measurements of flames and being able to extract the smoke point. So I think it's like the yield index that Yale does, and then they translate it over. So the work that, so this is like Charles McAnally, and you know, the work that they're doing at Yale, that's more closer to the flames that I model. But they have to translate that to the more industrial relevant measurement, which is a smoke point. Yeah. The molecules they're looking at, especially the Yale group, are a wide range of molecules, many of them that probably there's no mechanism, gas phase mechanism, so we couldn't model all these flames because we don't have the chemical mechanisms for these some of them very exotic fuels. Terpenes, I think, was a poster that was up yesterday.
Okay, last call for questions. Okay, so we actually are a little bit over time. But I want to thank Murray for giving us a wonderful talk. And Murray, we want to present you with this certificate for not only the talk, but also writing a nice review paper for us for the future.
Thank you very much. Oh. Thank you.
Thank you so much.
Did it go okay?
Awesome.
Yeah. Good.
Nice job.
Good.